Okay, this example, we have a force versus position graph. Now there's some implicit assumptions here. Maybe the force is in the direction of motion and so forth. But let's look at how we might interpret the slope or the area under a force versus position graph. Now we have forces of 1.4 newtons, positions in meters. Force of 8 newtons at a position of 1.4 meters and 18 newtons at a position of 5.7 meters. As usual, we're going to let's zoom back a little bit here so we can see this a little better. As usual, we're going to assume, for lack of any other information, that the force versus position graph is linear. And if we find the area under that graph, we see position goes from 1.4 meters to 5.7 meters, so that we have a change in position in this region. That's the width represents a change in position from 1.4 to 5.7 meters, which is a change of 4.3 meters. The average altitude of this graph will be the average of the 8 Newton force and the 18 Newton force. If you average 8 and 18, you add them and divide by 2, you get 13 newtons. So the average altitude of the graph is 13 newtons. The area is the average altitude, 13 newtons, multiplied by your displacement, 4.3 meters. And that equals 13 times 4 is 42, and 13 times 0.3 is 6.9. I guess that's 48.9 Newton meters, or 48.9 joules, which is the result that I'll circle to indicate that that is what the area represents. So that the area appears to represent average force times displacement, which is the amount of work done between those two positions. Now there's an assumption, as we say here, that the force is in the direction of motion, or that the force is directed along the x-axis at least. So if the force is directed on the x-axis and the points represent force versus position, then this is our best estimate of the amount of work done, again assuming a linear force versus position